The last topic in this section is the idea of weight. Now, you might think that we've already talked about weight, given that we've already talked about mass and gravity, but we actually are going to define weight a little bit differently. And this is something that I'm going to use the same definition as the book here, and I specifically want to point out that this is likely to be a different definition than what you've used in previous physics classes if you've had them. And the reason we're using this is so that later when we're talking about certain phenomena, it's clear what we mean when we say weight, that otherwise it might seem like you're referring to two different values as weight at the same time. So the basic idea is that we are defining weight to be what you measure on the scale. That's all. So weight is what you measure on the scale. So in the next slide, I'll talk about why that might sometimes not be what you expect. So most scales, I initially talked about balance scales, but most scales that are not balance scales, pan balances, or inertial scales, use effectively springs. Digital scales use a digital equivalent, but basically this is all about something that either stretches or compresses, right? So it compresses in. So what a scale does is not actually measure mass. And again, this would be like a pan, not a pan balance, but like a pan lab scale or a hanging scale. These are actually measuring how much the spring compresses. So when you make your measurement, you're actually measuring this. And so what's going on in this free body diagram that's on top of the sketch is that our object is this box. We're placing it on the spring scale, so initially our springs were higher. But the object pushes down, which compresses the springs. We haven't learned about spring forces yet. They're actually a lot more complicated than the forces we're talking about. You should understand the notion that if you compress a spring, it pushes back, though. So this compresses the spring, which is then pushing back. So we understand that we have the force of gravity down, and we know that that's going to be mass times gravity. But what is the acceleration in this case? Our acceleration, once it's just sitting there, is equal to 0. That means that our F net is equal to 0. So the only way that that can be true is if our spring scale force, the force from the spring pushing up, is equal and opposite to the force of gravity pulling down. So the point here is that we are measuring what's happening with the spring, and normally that is just exactly what the force of gravity is because net force is 0. And I'll come back to this on the next slide. So there are these scales we use sometimes in physics class that have springs in them, and the way you're measuring masses out is by just seeing how much this plastic thing here moves down, and then you read off what the mass is, and in this case it's in grams. But the trick is here, you're not literally measuring mass. You're actually measuring a force. It's just divided out gravity, assuming that that is the force you're pulling against. On the other side, it measures in newtons. So a spring scale is kind of a trick in that really it's telling you how far you've pulled or pushed a spring. The people who make it can know what that means in terms of forces, and then they can just divide out g to get the mass. So this is not just a physics scale, this would be like a real commercial scale. And again, there's a spring hidden on the inside. You don't see the spring. But when you go to make the measurement, there's just this little plastic thing here. And as you pull down on this stretches the spring and it ends up pulling somewhere. And so then you would read that off as the mass. But if you just pulled by hand, you would get a value. And clearly, that isn't the mass of your hand, that's telling you how hard you've pulled. So the point I'm trying to make is that scales actually measure forces. And you're not literally measuring the force from gravity, you're measuring the resistive force, the force that is opposing it. So scales are kind of tricking you in a way in that they might report a mass, but they've actually measured a different force, assumed that the gravitational force is equal to it, and then divided out g. Why does this matter? The whole point is that in physics class, weight does not mean the same thing as mass. Weight means this measurement. And the point being that the measurement of a scale doesn't have to be the same thing as mg. So let me show the one example where we need to talk about weight being different than mg. So imagine that a person is standing on a scale, and this can be just like a normal bathroom scale. We're not talking about anything fancy or strange here, in an elevator. Normally, that scale has a reading which is determined due to mg, and again, these two forces being balanced. However, what happens when the elevator that the person's in accelerates upwards? So let's talk through this. If we have an acceleration that's upwards, right? Basically, the elevator's accelerating upwards, so the person must be accelerating upwards as well. That means you have a net force that is upwards as well. So when we go to our free body diagram, we say the only forces acting on our person, right? In this case, our object is the person. We have the force of gravity down, fine. And we have the spring scale, right? So this is what the scale is basically measuring. It's pushing up. This is the spring pushing up. So if we need a net force that is upwards, the only way we can get it is if the spring force is bigger than gravity. So what this means is if you are standing in an elevator that is accelerating upwards, what your weight measures, what the spring scale tells you, is actually larger than mg, what you would get that way. If the elevator was accelerating downwards, your acceleration vector is flipped around, F net is flipped around, and now your spring scale force is smaller than the force of gravity. Oops, another typo. That's what happens when I copy and paste. Sorry, it should be like that. So the reason we're saying this is, again, m times g is something very fixed. So when we talk about the gravitational force on an object, all you need to know is what planet, or sun or star, what have you, the object is by. If it's by Earth, you know it's mg, done. That is always the force of gravity. We're using weight to mean what you would measure if you had your object hanging from a spring scale, or in this case, on top of a spring scale. In cases where acceleration is 0, that means your net force is 0, and in that case, weight is equal to your gravitational force. But if you have a net force and an acceleration, that's not necessarily the case. So that's why we're using the term weight to mean this very specific case. And so please be careful. Please don't just use W to mean mg. I know many physics classes teach it that way, but you're going to see problems on Mastering Physics or from the book where it specifically says things like, what will the weight be? And in that case, it doesn't mean mg. It means the measurement from a scale.